Now that we've kind of laid down the theoretical groundwork for Young's double-slit experiment, we want to start looking at the mathematical analysis from this. So in this mathematical analysis, it's going to be a little bit detailed. In some parts, it's going to be a little bit hand-wavy. At the end of the day, if it doesn't quite, resonate with you, don't worry too much about it. You're not going to be tested explicitly on the details of the analysis. There's a couple little things. There's about one or two little things I may flag for importance, but kind of bear with me on this. It's a really abstract. It's a bit of an abstract derivation, but we're going to go through with it. Now, what I'm going to do is I'm going to have my interference pattern here, and I'm going to just pick the first bright fringe. Why I'm picking that, I'm having no real justification for it. We're just going to pick it. Now, the two slits here we're going to call S1 and S2, and then the point on the fringe, or the center of the fringe, we're going to call that P. So this path from the first slit to this point P, we're just going to call that S1P, and then from this second slit to this point here, we're just going to call that S2P. We need that for a little bit later. Now, as we talked about in Young's experiment, the wave that's approaching the slits is going to be in phase, so S1 and S2 are going to be in phase with one another. And we know that the distance between these two slits, we're going to call that distance here D. Now, as we talked about, there's kind of two key terms we want to look at here. We want to look at path length versus path length difference. So the path length is this S1P and S2P. These are our path lengths. Like, this is the actual distance the wave has to travel. So in this case, S1P we're told is 10 wavelengths. S2P we're told is 9 wavelengths. The path length difference is just the actual subtraction of the two paths. So between these two paths, the difference in path length is 1 wavelength, which is consistent, we said, for the first fringe, bright fringe. For constructive interference, we want that difference in path length to be 1 wavelength. So let's start to look at this in a little bit more detail. And we want to use that condition for constructive interference. So I may flip back and forth between these two pages just a little bit here. So the first thing that we want to know, or that we know, is that difference in path length that we have here. So this difference in path length for the first bright fringe, we know that is just 1 wavelength. Now we could extend this out more generally. What we could say is, well, we could call some point S1PN and S2PN. This is the difference in path length to some from the first slit to any fringe, and the difference and the second slit to any fringe. So N is going to be this fringe order. For this first one here, we treated this as P1, like the first fringe. I could do this for any old fringe, the second, third, and the fourth. What we're just trying to establish here is that the difference in path length is going to be equal to an integer multiple of the wavelength, just to get constructive interference. We're going to clean this up, but the main thing we want for constructive interference is we want that path length difference to be some integer multiple of the wavelength. 0 wavelength, 1 wavelength, 2 wavelength, so on and so forth. Now, we're going to kind of look at a bit of a geometrical analysis here. Now, we have our two slits here. Here's my first pass, so this is my S1P here. Here's S2P, S1P, S2P. Now, if I take that difference between S1P and S2P, this is going to be my difference right here. Now, we could certainly pull out all the stops here. Like, this is not a right triangle, but surely we could do something like cosine law or sine law or some nice trig technique. But we're in high school physics, and we're not lazy. We just like to work smart and more efficiently. Is there a way that we could get a right triangle? The answer to that is yes, but we have to do something a little bit, well, we'll call it nefarious. Now, for the most part, this assumption works out okay, but understand that it does have some limitations. So this is assuming that our screen is quite close to the slits. Well, if we decide to take the screen, instead of having it here, we just move it far and far and far and far away, or, we say it's infinitely far away, what's going to happen is the farther and farther we move this away, the more likely that these two paths are going to end up being parallel with one another. And then what's going to happen is, well, if we do that, that difference in path length is still going to be here. But if we make the screen really, really far away, what we can actually do is we can establish a right triangle. And that's really convenient because right triangles are nice for us. So then we have that right angle here, we have that distance between the slits, we have that difference in the path length, and then we have this angle here. So this angle we'll talk about a little bit more later. We're going to do a little bit more hand wavy. But the key thing here in our diffraction equation that we're going to get, the big assumption is that we are assuming the screen is really far away, and that's important. Now, we're assuming it's infinitely far away. Obviously, we can't do that. So for practical purposes, we're just saying it's really, really far away. So that difference in path length here, this distance S1x, we can relate that difference in path length to this angle and to this distance between the slits. So what we've actually done is we've said, and let me go back to my diagram here. I know that this difference, this is my opposite side. This distance between the slits here is my distance, is my hypotenuse. So I have an opposite and hypotenuse. So I know the sine of this angle is equal to the difference in path length divided by the distance between the slits. And that's what we've put in here. So we've put that sine of that angle is equal to this S1x divided by d, or that difference in path length over d. Now, if you've kind of gotten to this point, you're doing really well. Now, here's where we're just going to start to adjust it for what we need. We know that for constructive interference, in order to have constructive interference, we need that difference in path length to be an integer multiple of the wavelength. So instead of writing out the words difference in path length, we're just going to say, well, sine of the angle is n lambda over d for bright fringes or constructive interference. Now, on the data sheet, that will be written in terms of the wavelength, so we could rearrange that for the wavelength and say this is d sine theta n divided by n, which is our fringe number. Now, of course, you may really want to ask, well, what is this theta n? You've just kind of introduced it and then just, went with it. And that's fine, and that's fair, a point to ask. Well, what we're going to say, and this is really hand wavy, like I'm just kind of saying this, without proof and all that. So I apologize if you want more of the details on this. Again, I've said this before and I'll say it again. The internet's your friend on this one. So that's the angle we've defined there. What we also notice, or the angle that we actually really care about, is that angle between the line that joins the center of the slits and the central maximum, and the center of the slits and the point in question. So we're looking at that angle there. This angle here and this angle here, if our assumption holds that PN's far away, these two things are going to be the same. This is what I'm not actually justifying. Take me at my word for this, even though that's not something I like to encourage. Just trust me on this one. Now, this angle here, this angle between the bisector and our actual path to the fringe, this from the midpoint, this is what we call our angle of diffraction. So that theta n that we've just randomly introduced, this is what we are going to call our angle of diffraction. So the angle of diffraction will always go between the midpoint and the central maximum, the line that joins this, or sorry, let me rephrase that. The angle of diffraction will always be the angle that is created between the midpoint and the central maximum, and the midpoint being between the two slits, and the midpoint and the point under investigation. That is our angle of diffraction. That's what we're going to be looking at exclusively. Now, somebody might say, well, we've talked about constructive interference. What do we do for destructive interference? Well, have no fear. We kind of go back to the same thing. Sine of that angle has to be the difference in path length over d. If you want destructive interference, you want that difference in path length to be some integer multiple of the wavelength. Or sorry, half integer multiple of the wavelength. So we can do that right here. We could say sine of the angle is this n minus 1/2 lambda over d. So this is our condition for destructive interference. You'll notice this time though I've set n belongs to the set of natural numbers. In this case we're doing for destructive interference, we don't want to do n equals 0, we want to do n equals 1, 2, 3, 4, so on. We basically don't want 0 in this case. But that's how we get our equation for destructive interference out of all of this. Or if you'd like to put it in terms of the wavelength, lambda equals this d sine theta over n minus 1/2. Now this equation for destructive interference isn't on the data sheet. The one for constructive interference is. In most of my time teaching Physics 30, I haven't really seen any questions on the diploma exam talking about destructive interference. So having only the equation for constructive interference, you'll probably be A-okay. In all of those equations, lambda is going to be the wavelength of light, d is going to be that distance between the two slits, theta is going to be the angle of diffraction. I don't know why that says meters there, that should say degrees. Sorry, I do tend to have typos when I try to fix my notes a lot, but sometimes I miss the obvious typo here and there. So yeah, angle of diffraction should be in degrees, and then n, this is going to be my fringe order. So which fringe I'm looking at, it doesn't have any units. So to summarize, my equation in terms of wavelength, my equation for constructive interference is this lambda equals d sine theta over n. And then my equation for destructive interference is going to be d sine theta over n minus 1/2. At the end of the day, are you going to be tested on how these are derived? No. But the only thing you have to understand for these equations are a simplification. They are built on the assumption that the screen is really far away. Or rather, it assumes it's infinitely far away. That's not going to be possible, so these results are going to be a little bit inaccurate. Now, broad picture, they're still going to give us great results, but you need to understand with our model, this has some limitations. And that's one of the things we always want to understand in physics. What are the limitations of the model, or what are the limitations of the equation we're using? We'll show you how to actually use this over the next few videos.